For the second question, we're going to determine IT and I1, which I haven't labeled here yet. So IT, you don't really need to have it labeled anyways. It's just a total resistance. So it's a total, sorry, not the total resistance, it's a total current. The total current that's entering the system of resistors and then coming back here. So that'll be IT. And then I1 is labeled over here. So let's start off with IT. IT is really easy. From the earlier problem, we found out that the total resistance of the circuit was about 30 ohms. We're just going to use 30 ohms for now, just because it'll make the calculations a little bit easier for us. So let's just say that we got a nice clean answer, and the resistance total was equal to 30 ohms. And we know that the battery is equal to 30 volts. Well, what's the current that's leaving the battery? All of that current is going to travel along and go through this resistor, right? So the current total is equal to the current that goes through this resistor. Okay, so the current through a resistor, well, we know a formula that has something to do with resistors. It's V is equal to IR, which is the voltage drop across a resistor. So the voltage drop across our resistor here is equal to the current that's moving through the resistor multiplied by the resistance of the resistor itself. So we can just fill in the values that we do know right away. We know that the resistance is going to be 30 ohms, and the current that's moving through the battery, through the resistor, the current that's moving through the resistor is IT, right? It's the total current. So we can just change I to IT, and that's the thing that we want to find the value for. Now, how much voltage is being dropped across this resistor? Well, since it's the only resistor in the path, whatever the voltage of the battery is has to be the voltage that drops across this resistor. So an electron that's leaving this battery, along its path, it needs to lose all of its voltage. And if there's only one resistor, then it's going to drop all of its voltage across that resistor. So the voltage drop across this resistor is just the voltage of the battery, which is 30 volts. And we're going to have IT, the thing we're solving for, 30 ohms. If we solve for IT, then what we're going to get is just 1 amp. And that's the answer for that one. So easy peasy. Now let's try to find the current for I1. So I'm just going to clean up a little bit, and maybe I'll get rid of this for now too. Okay, so for I1, I1 is the current moving through this resistor over here. Okay, so from our previous question, we know that the current IT is going to leave the battery. It's going to travel along this line. It's going to move down this resistor. It's going to move down this resistor, and it's only going to move down this line because, well, it could move down this line over here like that, but the electricity is only going to move down this short circuit because there's no resistance along this line here, right? So it's going to totally circumvent this network of resistors. Now that might be a little confusing to you, because you might think, well, okay, why does the electricity even bother going down this way then? If it can just go through this one resistor here and then go down here like that. Certainly this would be less hassle than going through these paths and then reaching down here. That's a really good thought, if I do say so myself. The reason why it's going to do that, the reason why it's going to behave the way that I'm explaining it's going to behave, where it comes out of the battery, goes here. Well, let's think about it a little bit. So it comes out of the battery like this, and remember this is one big node here, right? So this is one big node. Okay, so if that's a big node, basically what happens is it reaches this node, and it has three options. So we can go through this 15 ohm resistor over here. It can go through the 10 ohm resistor over here, or it can go through this 8 ohm resistor over here. So it has to go through one of those paths, right? So it will go through, the electrons. Some of them will go this way, some of them will go this way, and some of them will go this way. Okay. This 15 ohm resistor and the 10 ohm resistor, they come back together over here at this node. So that's that node that I've drawn right here. Now, as they move along the 8 ohm resistor, they get to another node like this, and they have two options, right? They can go through this 15 ohm resistor, or they can go through nothing, right? So of course they're going to go through nothing, right? They're not going to go through this 15 ohm path at all. Then over here they have an option of going through a 15 ohm resistor, which is this one over here, or they can go through nothing, right? There's no resistance here, so they're not going to go through this 15 ohm resistor at all. Then they come down here and they have the 7 ohm resistor, 7.5 ohm resistor, and they have nothing. And of course they're going to go through nothing, right? So that's why they're not going to go, the electricity is not going to go through this big network of resistors. It's just going to go through these 15 ohm resistor and this 10 ohm resistor, and then it's going to go straight down to this 12 ohm resistor. Because when it gets to the 12 ohm resistor, right, when it gets here, the electricity, it has no choice but to go through the 12 ohm resistor. There's no other option here, right? Okay, I'm going to pause here for a second. Okay, so the point I want to make here was that when the electricity moves out of the battery and comes along this way, it gets to this node over here, and it has three different ways that it can go. So it can go through this resistor, it can go through this resistor, it can go through this resistor, and if it goes through this resistor, it's going to go down like this. So we can redraw this diagram to make answering this question a bit easier. So I'm going to delete this, and I'm going to delete all of these because remember, the electricity is not going to go through that way anyways. Okay, so we've got this kind of situation going on here. And what else I'm going to do is I'm going to put this resistor together with this resistor here. So remember I said you can just you can slide it down and combine them together. So you can take this one and slide it this way and slide it that way, and you can put them together like that, and that's going to produce a 20 ohm resistor, because it was 8 and 12 to begin with. So the resistor down here was 12 ohms, and the resistor up here was 8 ohms. So when you put those two together, you're going to get a 20 ohm resistor. Ah, okay, I went too far back. Okay, let's clean that up. Alright, so we connect those wires like so, and we just label this one as 20 ohms. Okay, so we have this kind of situation going on, and the reason why I've done all of this is because I want to figure out how much of this current IT is going to go through here, how much is going to go through here, and how much is going to go through here. So what I'm going to do first of all is I'm going to combine all of these guys together, which might seem unintuitive at first, but you'll see why I do that in a second. So I'm going to redraw the diagram a little bit. So we've got this 30 volt source, and it's going to go like this, And I'm going to put these two resistors together. So, I'm going to put those two resistors together. So they're parallel resistors because they start off at the same node, which is this big white node up here, and they end off at this node over here. So you just use the formula to figure out what the equivalent resistance is going to be. So RT is equal to R1 multiplied by R2 over R1 plus R2. And that's going to be 10 times 15 over 10 plus 15. And somehow I know that's going to equal 6 ohms. So I'm just going to write that down. Okay. So that's going to be 6 ohms. Okay, then this one over here is going to be 14 ohms. This one over here. And I'm only going to draw this circuit up until the point where these two paths come together. So this other path over here is the 20 ohm path. Like that, and it comes back together like this. 20 ohms. Okay. What I'm going to do is I'm going to slide these guys together as well, like this. And it was 14 and 6, so that's going to equal 20. All right. So the reason why I did this is because I want to figure out how much of this initial current, the I total, so the total current, how much of it goes down this way and how much goes down this way. And when I know how much goes down this way, this 20 ohm path, then I'll have some left over here. Like I'll know how much goes down this way. And then I can split this off again and I can figure out exactly how much of this amount goes down this way and how much goes down this way, and that'll give us the answer. So that's just a preview of what's to come. So let's do this. So from our previous question, we found out that IT is going to be 1 amp. Not exactly 1 amp, but just for the sake of the example, we're going to keep it at 1 amp to make our calculations easier. And to figure out how much current is going to go down a single path, so let's say we want to find out how much current is going down this path, what we do is we use this formula. So the current down a path, a parallel path like this, right? It's going to be split off like this. So what you do is you take the resistance of the other path, RO, and you divide that by the sum of the resistances in the path. So what that means is, oh sorry, and there's one other thing. Then you have to multiply that by IT. Okay, so what that means is we're going to have, so the resistance of the other path is 20 ohms. And the sum of the resistances is just 20 plus 20. So 20 ohms plus 20 ohms. And so what we're going to get is 20 over 40. And sorry, I forgot IT again, which is just 1 amp. And move IT over here as well. And what you're going to get is 0.5 amps. So 2 over 4 is 0.5. 0.5 times 1 amp is equal to 0.5 amps. So that means that half, so over here, like we had 1 amp moving down, and half of that amp goes down this way, and half of that amp goes down that way. And that's kind of what you would expect, right? Because both the paths have the exact same resistance. Just as an example to you, you can skip this part if you're not super interested, but let's say, for example, this path over here was 40 ohms. So if that was 40 ohms, how much current do we expect to move through that path? Well, if you look at the total resistance, so if we look at the total resistance, it's 60, and this one has 40, or sorry, This one over here has 20, and then we get 1 over 3, and if we multiply that by the total resistance, that's going to equal 0.3 amps. So then 0.3 amps would go through here. Now you might be wondering where I got all those numbers from, so let me just do that a little bit more slowly. So remember, the formula was I is equal to the resistance of the other path over the resistance, the sum of the resistances. So the resistance of the other path is 20 ohms, and the sum of the resistances in this case would be 40 plus 20 ohms. And again, I forgot that this formula you need to include the incoming source. Sorry, the incoming current. So let's erase that. Yeah, I usually do this without memorizing the formula, so that's why it's kind of like this. So okay, so the incoming current, the total current coming into this parallel circuit is 1 amp. So that's why we put IT as 1 amp. This is going to equal 20 ohms over 60 ohms. That's going to be multiplied by 1 amp. And what you're going to end up getting is 1 over 3 multiplied by 1 amp, which is equal to 0.3 repeating amps. So 0.3 repeating means 0.3333, which is equal to 1 over 3. Okay, so anyways, that's just a bit of a detour, but now we know that 0.5 amps goes down this way. Okay, and that means the since IT, the incoming the incoming current into this parallel circuit, and this guy over here is 1 amp, we have 0.5 amps left to spread across these two resistors. Okay, so 0.5 amps has to be shared between the 15 ohm resistor and the 10 ohm resistor. Okay, so that's pretty straightforward. To figure out how much current goes down this 10 ohm resistor, we just use our formula again. So current is equal to the resistance of the other path over the sum of resistances. In this case, the resistance of the other path is 15 ohms. And of course, I forgot the incoming currents. So the current that they need to share in that case is going to be 0.5 amps, right? So the current is 1 amp, but we know that 0.5 amps goes through this 20 ohm resistor, and we have 0.5 amps that go down these other two paths, and that needs to be split. So the total current that's going into this parallel path is 0.5, so that's why 0.5 is the value here. So I'm gonna delete all this, and we're gonna continue with the equation. So the sum of the resistances is going to be 15 plus 10, right? So there's 10 ohms here and 15 over here, and we're going to multiply that by 0.5 amps, and what we end up getting is 15 over 25 times 0.5, and that's going to equal, well, it's going to equal 15 over 50 amps, and that's just going to equal 30, sorry, 0.3 amps. So that's just some mental math, but yeah. So now we know how much current is going to go down this resistor over here, which is what the question's asking for. So 0.3 amps.